Hello everyone, in this video we have to see about some of hexagonal close-packed, that is important parameter we have to calculate. So let's recall about previous class. We have to see about the sum of the simple cubic and body center and efficiency stretches. From that we have to calculate the sum of atomic packing factor, atomic radius and atomic density, how it varies from the simple cubic and BCC and efficiency stretches. Today's topic to discuss introduction to the hexagonal system and atomic packing structure and how it is used in the device fabrication methodologies. So close-packed structure will be used for we have to study some of the density calculation, X-ray diffraction and the correlation with thermal properties, analytical properties and comparison with the structures, and there is atomic announcement understanding. So these are the possible for that from that any of the crystal structure, especially hexagonal close-packed structure. So here that we have to calculate that unit cell of diagram of the primitive hexagonal structure, that is the A equal to B not equal to C, and you can see that three layers of the arrangement of atoms in the hexagonal structure. There is a bottom and upper layer, immediately have three layers and six faces, each corner have an atom, and center of the base and top layer will be the center atom present in this unit cell. So this is the coordination number is nothing but nearest neighbor. You can see that the hexagonal close-packed structure having the number 12, that is the bottom layer, middle layer and upper to the upper layer of that particular unit cell will be n and n plus n means number of nearest neighbor across by the n. So it will be a 12 numbers of the atom. Any atom you can take from the hexagonal unit cell, it connects 12 nearest neighbors. So a coordination number of the hexagonal structure will be 12. So here that you can see that about the unit cell and close packing structure and unit cell diagrams, the radius of the atoms, the cutout mark of the atoms present in the unit cell. We have the hexagonal cell, how it is the atoms will cut in partially shown in these figures. So these are the calculations. From that we have to calculation. See, there is a small difference between that. We have to calculate the unit cell volume. Before that we have a C is not equal to A and B. So A and B in x1 direction is equal, not in this direction. So the ratio between that C to A, it will be a root 8 by 3. That's that with the residual lat, that is the ratio of C by A, that is the axis difference along C and axis to the value of root 8 by 3. It's about 1.633 values. So this is the diagrams that we have to calculate the volume. From the derivations we have seen that finally we have to see atomic packing factors. It's about 72 or 74%. So 74% shows that atomic packing factors of totally highly tightly packed structures of hexagonal structure atom in the hexagonal present system. So this is our derivation. First you have to calculate that area of triangle. So when we take the base, this is separated by the 6 triangles. So we have to calculate the base and height of the area of the base equal to the triangle, 6 triangles. We have they are divided into 6 triangles and find out the area of the base and multiply by the h. We have to calculate the volume. So total volume of the HCP cell will be 24 root r by r3. So then next we have to apply the radius, atomic radius is about a by 2. That is the side of the atom in the 6 faces, 6 hexagonal faces will be the a by 2. So from that we have to calculate the volume of atom, the ratio APF. That is we have to put the formula, volume of all atoms and volume of the unit cell. We have to calculate the APF about 74%. It shows that it is highly densely packed compared to any other crystal structure, that is SCC, BCC and FCC structures. So that is the highly packed structure, about 74%. Remaining only 26% will be the empty space of the remaining atoms. So what is the use of that? Mainly we have to calculate that orientation. From the orientation we have to calculate through the Miller indices differently we have to cut it and used for physical properties. From that, where is the direction? Miller planes will direct the atomic density. From that atomic density calculations and Miller indices give the specific physical parameter on particular crystal structure and particular direction. So it is mainly depends on that atomic density along particular directions and we connect that with the physical parameters. So what is the summary? We have to calculate that there is a unit cell atoms, volume of the unit cell, parameters related with this unit cells, and we have to calculate the volume of single unit cell and total volume of the unit cell and compare that ACC and FCC structures. So in this video, let's summarize a short review on that hexagonal close-packed structures. So here I show some of the reference about that hexagonal close-packed for your study. Herewith I stop here. Next week I will discuss about the interesting topic on next videos. Thank you.